In the last couple of videos, we took a look at some techniques for evaluating limits. And we took a look at a technique by using a table of values to see where what value the function approaches from both sides. And we also took a look at a graph to determine what value we're approaching from both sides to evaluate the limit. In this video, we're going to take a look at two more methods to evaluating a limit algebraically this time. So the first method we're going to take a look at is called the dividing out technique. The dividing out technique. So let's take an example problem so we can take a look at what exactly we're doing with the dividing out technique. So we have a problem. Evaluate the limit as x approaches 3 for the function x squared minus 8x plus 15 over x minus 3. So initially what we're going to try to use is we're going to try to use direct substitution to see if we can evaluate this limit. So if we do that, if we use direct substitution, we get 3 squared minus 8 times 3 plus 15 over 3 minus 3. And what that gives us is we get 9 plus 15, which is 24, minus 8 times 3, which is also 24. So 24 minus 24 is equal to 0. On the bottom, we get 3 minus 3, which is also equal to 0. And essentially, this form, 0 over 0, is what we call an indeterminate form. An indeterminate form, which means that we can't really determine anything from the value 0 over 0. 0 over 0 doesn't really mean anything. It's undefined. We're dividing nothing by nothing. We can't evaluate the limit from this form alone. So this is why we are using all these different methods to evaluate the limit, because we can't do anything with this indeterminate form. It doesn't tell us anything. So because of that, what we're going to try to do is we're going to use this technique called the dividing out technique to see if we can get a value that is not the indeterminate form. So the way we're going to do this is we're going to take a look at why we get this indeterminate form. So when we have a rational function and we get the indeterminate form 0 over 0, so we get 0 in the denominator as well as 0 in the numerator. What this means is that there is a common factor in both the numerator and the denominator. And this is the reason why we're getting 0 over 0. So let's take a look at that. So if you can factor out the numerator right here, what we get is we get x minus 3 times x minus 5 over x minus 3. So we see that there is a common factor of x minus 3 in both the numerator and the denominator, and this is the reason why we're getting the indeterminate form 0 over 0, because when we plug in 3 for the numerator, we get 3 minus 3, which is 0. 0 times anything is going to be 0, so that's why we get 0 in the numerator. And then we have 3 minus 3 in the denominator, which is why we get 0 in the denominator. So we know that there is a common factor in both the numerator and the denominator. So what does this tell us about the graph? Well, this tells us that there is going to be a hole in the graph. So if you studied rational functions, you know that if we have a common factor and we cancel this out, this is how we can solve for rational functions and how graph rational functions. This common factor basically means that we have a hole. So essentially what we have is this function, when we graph it, it looks something similar to this. We have a normal linear function x minus 5. We have a normal linear function x minus 5, except that the value of x equals 3, 1, 2, 3, this value is going to be undefined. There is no value at this particular x value domain. It's just undefined. The graph just stops and then starts again here. So it's a linear function with the exception of a hole right here. So what we're doing is, by canceling out this common factor from both the numerator and the denominator, we're getting an equivalent function. An equivalent function whose graph looks exactly the same as the original function, with the exception that the value at x equals 3 is now going to be defined. There is now a value when we plug in 3 into this new function, because it will not give us the indeterminate form. So because of this, now what we can do is we can use direct substitution. We can use direct substitution. So if we plug in x, we're trying to find the limit of 3. So if you plug in 3 minus 5, because it's x minus 5, 3 minus 5 is equal to negative 2. So we can evaluate the limit now. We're getting a value that is not the indeterminate form. So the limit of, as x approaches 3 of, let's call this f of x, it's going to be equal to negative 2. Alright, so that's our first method for evaluating the limit. Now let's take a look at another technique. And what we call this is, we call this the rationalizing technique. It's going to be easy. Rationalizing technique. So essentially what we're going to do is we're going to use this for a different type of function. For rational functions, we can use the dividing out technique because we have something in the numerator and denominator we can cancel out. For the rationalizing technique, usually we're going to use this for root functions, so square root functions of the like. We have the function, the root of 4 plus x minus 2 all over x. We want to find the limit as x approaches 0. Okay, so again, we're going to try to use direct substitution, and when we do that, we get the root of 4, which is 2 minus 2 over 0, which is equal to 0 over 0. And again, we're getting this indeterminate form, and we don't like this indeterminate form. We want to get something other than this indeterminate form so we can determine what the limit is going to be. So for these types of functions, we're going to use the rationalizing technique. And the way we're going to do that is we're going to try to rationalize the numerator. So we're all used to rationalizing the denominator because we can't have roots in the denominator, right? So we're going to try to multiply by the conjugate and basically get the roots on the numerator and then have the denominator free of roots. Here we're going to do exactly the opposite. We're going to try to get the roots out of the numerator and try to get them on the denominator. So the way we're going to do that is we're going to multiply by 1 in the form of the conjugate of the numerator. Now the conjugate is basically something that is the opposite to this. So we have two terms. Actually, we have two terms over here. So we have the root of 4 minus x, and we have negative 2. When we're multiplying by the conjugate, it's going to be the same two terms, except it's going to be the opposite sign. So it's going to be the root of 4 minus x plus 2. And because of that, we essentially now have a difference of squares. So we have 4 minus x, the root of 4 minus x squared. So this is going to give us the root of 4 minus x squared minus 2 squared. So this will cancel out the roots. So since we're multiplying by 1, however, this has to be on both the numerator and the denominator, because anything over itself is going to be equal to 1. So if we put this on the numerator and the denominator, it's the same color, over x, we're multiplying both the numerator and denominator, we get the expression, we get this, which is 4 minus x, because the square root and the squared are going to cancel each other out pretty much, minus 2 squared, which is equal to 4, all over x times, I'll use the same color here, the root of 4 minus x plus 2. And we can further simplify this by 4 minus 4 is equal to 0. And so we have negative x over x times the root of 4 minus x plus 2. The x's essentially cancel themselves out. So we're left with the simplified version, negative 1 over the root of 4 minus x plus 2. And now we can be sure that we're not going to get this indeterminate form again. We're not going to get that indeterminate form again because on the numerator we're going to have negative 1 no matter what. We're never going to have this 0. So if we try direct substitution now, again, direct substitution, we're going to get, we're substituting 0, so we get negative 1 over 4 minus 0 is 0. The root of 4 is 2 plus 2, which is equal to negative 1 4.